This is a review of how DNA fingerprinting works. It's called DNA fingerprinting not because it has anything to do with your fingerprint, but because, like fingerprints, no two people have identical DNA. So here I have two people and 8 nucleotides of their DNA that are not identical. You can see the last 3, or the second to last and third to last, are different. In real life, people's DNA is very, very similar, way over 99.9%, but if you get strands that are billions of nucleotides long instead of 8 nucleotides long, you would be able to see the differences. The first thing that happens in DNA fingerprinting is that something called a restriction enzyme comes in and cuts at a very particular place. Here, let's say the restriction enzyme cuts between every T and A. So for the person 1, it would be cut here and here. For person 2, it would be cut, the same strand would be the same, but the other one would be different. Now, note that we didn't actually see this happen to our DNA fingerprinting. This happened long before we actually got started. What we had was liquids of DNA that had already been cut by a restriction enzyme. But because no people have identical DNA, you end up with different lengths of strands based on where they're cut. So person 1 will have a strand that's length 3, length 4, and length 1. Person 2 will have strands that are length 3, and length 2. So, in real life, you can think of 3, 4, and 1 as being thousands or hundreds of thousands long, but it's the same basic idea. The next step, and this is where we started, is we loaded the liquid containing all of that DNA into a gel. So we could load all of person 1's DNA into one well. We could load person 2's DNA into one well. And then we would load the DNA from the crime scene into a third well. Just like with fingerprints, the goal is to match up the DNA from the crime scene to someone's DNA that we have on file, or in this case, that we got from the supply company. Then we turn on our electricity and run it through the gel. Remember that DNA is slightly negative, so it's going to run towards a positive. But bigger pieces take longer to go, or in other words, they will not go as far in the same amount of time. So all of the DNA starts running this way, but it's going to start running at different speeds depending on how big each piece is. Let's review. Person 1 has a long strand, the longest one of 3 nucleotides, and the shortest one overall. Person 2 has strands of 2 sort of middle lengths. So what would that look like on our gel? Well, it would look like this. Person 1 would have the strand that goes the least far, one that goes a little bit farther, and then the one that goes the farthest because it's only 1 nucleotide big. So to compare from the previous page, this is going to be the one that's 4 large, 3 large, and 1 large. Person 2 is going to have DNA that goes to the 3 distance. In fact, this could be a pretty big band because they've got 2 strands of that length. And they're going to have a DNA that goes to the 2 length. Again, 3 length is going to go farther than 4 because it's not as big. 2 is going to even go farther. 1's going to go the farthest. So now the last step is to figure out whose DNA is identical to the DNA from the crime scene. So let's imagine we got this pattern from the crime scene. That would let us know that person 1 was the criminal. If, on the other hand, you'd gotten the opposite pattern, it would have let us know that person 2 was. So what happened in the actual lab? Well, let's see. We loaded the 6 samples and let them run. I realized that we got different colors, but in this case, I'm going to use just one color for simplicity. Most of the samples turned into 2 bands. So one sample looked something like this. One sample looked something like this. I think the third sample may have been like this. The fourth sample looked somewhat like the third, maybe even had 3 bands. The fifth, and the sixth. Now, here's what's important. First, we need to identify which of these is the band from the crime scene. Remember, it was band number 2. The next question is, which of these bands is identical to the band from the crime scene? Well, I didn't do a very good job drawing it here, but in reality, it was number 6. This belonged to me, Josh. So, all you can see here is that Josh's pattern matches the crime scene pattern. That would be like saying Josh's fingerprints match the fingerprints found at the crime scene. We don't actually find Josh's actual fingers at the crime scene, much like we don't find pieces of DNA that are still on Josh, but you're finding matching DNA or matching fingerprints. So in the same way, since we found matching DNA, we can assume that the DNA from Josh is the DNA at the crime scene and that Josh is the criminal. What this also shows us is that, say, the restriction enzyme cut Josh's DNA into 2 segments, like it did at the crime scene, whereas maybe person 4 was cut into 3 segments, so had more of the spots where the restriction enzymes were going to cut. Josh's segments were also on the smaller side because they ran farther than, say, some people. But the most important thing, again, is that you're looking for a match. Much like fingerprints, you're looking for a match between the crime scene and the person who we believe committed the crime. Since everyone's DNA is unique and will be cut in unique ways, there should only be one match, and in this case, there was only one match, and that was me.
Made with Doodlecast Pro.